Hi, this is Claire Wells. Welcome to my presentation on homeostasis. So most of you probably already have some idea about what homeostasis is, and we're going to try to just reinforce that idea and go into a little bit more detail with it. So if you look at the word homeostasis, it comes from Greek. It's composed of two Greek words, homeo and stasis. Homeo means the same, and stasis means standing still. So when you put them together, it means staying the same. However, that's kind of misleading in a way because conditions in the body are never actually constant. They're never staying the same without changing. They're always changing at least a little bit. The goal of homeostasis is to make sure that they only change a little bit and not a lot. So homeostasis is basically about balance, keeping conditions in the body balanced so that the organism can survive. You can define homeostasis as how an organism's body maintains stable conditions that allow it to live, or you could define it as the tendency of an organism or cell to regulate its internal conditions, such as the chemical composition of its body fluids, so as to maintain health and functioning regardless of outside conditions. Or you could define it in another way using different words. But these are all definitions basically meaning that conditions in the body are maintained so that life is supported. The word homeostasis actually was first used in 1926 by Walter Cannon, a doctor. The concept is older than that. It had been introduced in the 1800s by another doctor, Claude Bernard, but he used a different term for it. And the word didn't become popularized until 1932 in Walter Cannon's book, The Wisdom of the Body. Just FYI. So homeostasis is maintaining essentially all of the conditions in the body that are critical for life. Some of those conditions would include the temperature, your blood pressure, the pH, or how acidic or basic your body fluids are, the water content of your body, oxygen levels in the blood, carbon dioxide levels in the blood, the concentration of different ions in the blood, prominently sodium, chloride, calcium, and potassium, but also others, the concentration of sugar in the blood, and sugar in the blood is always in the form of glucose, the concentration of different amino acids in the blood and fats in the blood, and also micronutrients like vitamins. So not literally everything that you need for life is controlled by homeostasis. So for instance, there are some micronutrients that are not controlled by homeostasis, but most of them are. Anything that is extremely important for your life will be maintained through homeostasis. So homeostasis is really important for for all organisms, of course, but especially for multi-celled organisms. Our bodies are basically like incubators that are maintaining all the perfect conditions for us to live in, and we're not able to survive if the conditions deviate from that norm very much. So if you have a single-celled organism, it needs to be able to survive different temperatures, like hot temperatures, cold temperatures, different water levels. It has to be able to live if it's in water or if it's on a dry surface. So it has to be able to withstand a lot of extreme changes in environmental conditions. Your cells are not like that, though. They're relying on the body to maintain precise conditions for them. You can't take a hot temperature and a cold temperature. You can only take 98.6 degrees plus or minus a few degrees. If you have like a 10-degree difference in your body temperature, you're probably going to die. This is because the body is able to maintain homeostasis so well that your cells have kind of lost the ability to do it all by themselves, the way that a single-celled organism cells can do. So it's similar to Goldilocks. Goldilocks liked everything to be just right. Just the porridge just right temperature, the cushion just the right softness, and your cells like everything to be just right as well. You can really see this whenever you're trying to maintain cells in culture that have come from a multi-celled organism. For instance, cancer cells. So, of course, we know that cancer is a very deadly disease, and if you have cancer cells in your body, it can be very difficult to destroy them before they destroy you. But when you're growing cancer cells outside of the body in culture in a lab so that you can study them, it's very different. It's actually quite easy to kill them, and you have to try very hard to keep them alive. They need the temperature just right. They have to have just the right amount of all the different ions in their media, just the right amount of nutrients in their media. The pH of their media has to be just right for them. If it starts to vary, they're going to start dying. You can't keep them out in the light too long. They like it dark. Everything has to be perfect for them. And not only that, but if you leave their little dish exposed to the air for too long, other things like little bacteria or fungal spores that are floating in the air will land in there and start eating the media. And those things are basically going to multiply and consume all the media and kill the cancer cells, because these single-celled organisms are much better at surviving than a cancer cell is if the cancer cell doesn't have a body. The cancer cells are depending on the body to provide the perfect conditions for them, and without those conditions, they're essentially they have no hope. So when you're maintaining cells in culture, your job is basically to be maintaining homeostasis for those cells instead of the body doing it. Normally the body would be keeping the right pH and the right temperature. You have to do that instead if you're maintaining cells in culture, and it's actually quite hard. It's very easy to have the cells die on you. So the whole point of your body is basically to maintain those homeostatic conditions in a way. The way that your body is structured, the anatomy of your body, and the way that your body functions, which is the physiology of your body, is all designed to maintain homeostatic conditions, so that your cells will have the temperature that they like, they'll have the nutrients that they like to have and the concentrations they like to have it in, and everything just the way they like it. You can actually view homeostasis as the basic goal of all the parts of your body. So of course your cardiovascular and respiratory systems are kind of maintaining the right concentration of oxygen and carbon dioxide in your blood and making sure that all the tissues get oxygen. So that's obviously related to homeostasis. But it can also be less obvious things like the skeleton and your muscles that don't seem obviously related to homeostasis. But if you get cold, you're going to start shivering. That brings your body temperature back up. So the muscles are actually important for helping you maintain your body temperature. And also, you need both your muscles and your skeleton to move. And you need to move to get food and eat it. And if you're not eating food, then you're not maintaining the right concentration of glucose in your blood and the right concentration of different nutrients in your blood, and you're gonna die. So from a certain perspective, any organ in your body can be seen as related to homeostasis in some way. Homeostasis is maintained by feedback loops. You have two basic types of feedback loops, positive feedback loops and negative feedback loops. The example in this figure is using stocks. In a positive feedback loop, you have some stimulus, in this case, the price of stocks rising, and then that causes a response. In this case, people who buy stocks buying that particular stock. So when the price goes up, people will start buying the stock because they're like, wow, that stock, that's making money. I want the stock that makes money. And then the response is going to cause the stimulus to increase even higher in a positive feedback loop. So in a positive feedback loop, you have a stimulus, you have a response, and then the response enhances the initial stimulus and makes it even more extreme or even higher. So the stock prices rise. Your traders buy the stock because they notice that it has a high price. And since everybody's buying the stock now, that drives the price even higher. So the price rises further. Then even more people notice that it's a stock that's on the rise, and they buy the stock. Since even more people are buying the stock, the price rises again. This is a positive feedback loop. It's going to produce higher and higher prices. So you have some positive, well, you actually have a lot of positive feedback loops in the body, and a number of them are used to maintain homeostasis. But usually homeostasis is maintained by negative feedback loops, which is kind of the opposite thing. So in a positive feedback loop, you have a stimulus, then a response. The response enhances the stimulus. In a negative feedback loop, you have your stimulus, you have a response. The response counteracts the stimulus and makes it go back the other direction. So this is maintaining more like steady conditions. So with reference to stocks, if the prices rise, if you're trying to kind of buy stocks smartly, then you are buying low, selling high, right? So when the price of your stock goes up, it's time to sell it. So when everybody starts selling that stock because the price went up, then the price is going to go back down. So the price falls. Then, since you're buying low, you notice that the price is low now, so it's time to buy. So everybody goes and buys that stock. Since everybody's buying it, the price rises, and now it's time to sell. So if you're following this negative feedback loop, the price of the stock is going to rise and fall, but it will remain overall constant. Whereas in the positive feedback loop, the price is going to get higher and higher and higher and higher until, of course, the bubble bursts, because they can't get high forever. So usually in the body, you're using a negative feedback loop in which your stimulus causes a response and the response counteracts the stimulus. That is the way to maintain steady conditions. So that's what your body usually uses to maintain homeostasis, which is steady conditions. You also have some positive feedback loops operating in homeostasis, but those are less common. So looking closer at the negative feedback loops, they have kind of stereotypical parts that we can talk about and that we can identify in every negative feedback loop. So first you have a stimulus that causes a change in a variable. In the previous example with stocks, that would be an increase in the price of the stock. Then that change has to be detected by a receptor. In the body, that would be something like a stretch receptor in the walls of your blood vessels, or a temperature receptor in your skin, an actual sensor that's sensing something about the world or about your body. But in the stock example, the receptor would be like the stock market. Like you can look on the stock market and see what the prices are doing. Then this information goes to a control center. The information from the receptor is going to get sent to the control center. In the body, that's usually the brain, but it can be other things also. In our stock example, the control center would actually be just the investor themselves deciding what to do. The control center is going to take this information about the increased stimulus that it got from the receptors. It's going to take that information and decide what to do about it. Once it decides what to do, it's going to send that command to an effector, which is something that's going to actually do it. So in the body, that would be frequently a muscle. It could be a gland that starts secreting something. Like for instance, if the temperature got too high, you would have sweat glands as the effectors that are going to start sweating so you can drop your temperature. So it can be different things. In our stock example, the effector is going to be, well, the investor, actually engaging with the stock market to sell or buy stocks. And then in our negative feedback loop, the effect of that effector is to decrease the variable back down to its normal level. So counteracting the stimulus. It goes up in the stimulus and it goes back down in the ultimate response, which would be like selling the stocks so the price goes back down. So this is kind of the same thing, the negative feedback loop broken down for specifically body temperature. So if your body temperature drops below the normal range, so here you have your normal range for body temperature centered around 98.6 degrees. If that temperature goes down because maybe you went outside on a cold day and you didn't wear a coat, you're going to have receptors that pick that up. In this case, those are temperature receptors that are found in the skin. Whenever the temperature goes down, they're going to start firing nerve signals, and that information goes into the brain, which is the control center. The brain is going to look at that information and decide what to do about it, and then it's going to send a command signal out, in this case to the skeletal muscles, and tell them to contract and then relax and contract, which is shivering. Whenever the muscles are doing that, they start consuming a lot more energy and having a lot more chemical reactions. They need chemical reactions to make energy and then to contract. anytime you have those chemical reactions going on, it's going to create heat as a byproduct. So when the muscles are contracting a lot, they start creating heat. And then that heat increases your body temperature back up to the normal range. So at that point, you're back to normal. The skin receptors will detect that the temperature is normal and send that information to the brain, and then the brain will tell the muscles to stop shivering. It'll also happen the opposite way. If your temperature went up instead of down, maybe you went outside on a hot day, that information will be picked up by the receptors in the skin. It gets sent to the control center, which is the brain, and the control center will decide what to do about it and send out the command to the effectors, which in this case would not be the muscles, but would be the sweat glands. Then you start sweating, and your temperature drops back down to the normal range. A thermostat works basically the same way. So if you have your thermostat set at 70 degrees, a nice temperature, and then the actual temperature in the room drops, you have a receptor, which is a thermometer inside of the thermostat. It's going to notice that the temperature has dropped below the set point of 70 degrees. It's going to send that information to the control center, which is a little chip inside of the thermostat. And then that chip is going to decide what to do about it and send the command out to the heater. It'll turn the heater on. So your effector is the heater in this case, and it creates heat, which raises the temperature of the room back up. And when it gets to 70 degrees, the set point, the thermometer detects that, the little chip detects that, and it turns the heater off. So in the previous example with the thermostat, I introduced the set point. The set point is the ideal value of a variable. So if you have set the temperature on your thermostat to a certain level, that is a set point. 98.6 degrees is also a set point. That's a set point for the temperature within your body. That's the ideal temperature that you would like to have in your body. Actually, you're not going to be at 98.6 degrees all the time. In fact, you're usually not going to be at 98.6 degrees. You'll be a little bit off from it. So homeostasis is not actually maintaining the variables precisely at the set point. If this is your set point here, 98.6 degrees for temperature, and then this orange line is your actual body temperature, you'll notice it kind of meanders around. It goes up, it goes down. It's always varying around the set point, but it usually doesn't spend very much time at the set point, but it also never gets far from the set point. So you're basically having negative feedback loops that turn on anytime the temperature gets too high or too low, away from 98.6, and then that feedback loop will nudge the temperature back to the set point, and then you frequently will overshoot it and go too far on the other side. Then you have a reverse negative feedback loop turn on, basically just trying to always return the value of the variable to the set point, but you never actually make it stay at the set point. So that's why we say in homeostasis, it's not actually literally staying the same. Your body temperature is not always literally 98.6 degrees, but it's always trying to be at 98.6 degrees. So it's always just fluctuating or hovering around it, going a little up, a little down, a little up, a little down, always around 98.6, never getting far from 98.6. So that's negative feedback in homeostasis, and that is the main strategy that the body uses to control homeostasis. But you also have positive feedback loops sometimes. The most famous example of positive feedback loops is uterine contractions during childbirth. That's actually not related to homeostasis really, but I will go through it here because it's the most famous example. So the way that works is that when you're going to give birth, you have the baby pressing up against the cervix, which is the opening of the uterus, and that stretches the cervix. And then you have some stretch receptors there that sense that you have that pressure, that stretch, and those stretch receptors are going to cause the uterus to release the hormone oxytocin. Then that hormone oxytocin causes the walls of the uterus to contract. So you have muscles in the walls of the uterus, and those muscles are going to contract. And that pushes the baby closer up against the cervix. So now you have more stretch on the cervix, and the stretch receptors are activated even more strongly. Then that's going to cause even more oxytocin to be released. That's going to cause an even stronger contraction of the uterine wall, and that's going to cause even more stretch on the cervix. So this positive feedback loop is going to repeat, always making the stretch of the cervix more extreme until the cervix gives way and you have a baby. So in homeostasis, we're always trying to hover around a set point. Positive feedback usually doesn't help you do that too much because it's just making some variable more and more extreme. But you do still have positive feedback loops sometimes that are kind of found inside. They're kind of lurking inside of a negative feedback loop usually, and their basic job would be to make it happen faster. So that if the body is trying to respond to a variable, moving away from the set point, instead of taking a long time for the body to respond using the negative feedback loop, you're going to have a tiny little positive feedback loop hiding inside of there that speeds up the response so that you're maintaining homeostasis more quickly. A good example of that is blood clotting. So here you have blood clotting. If you have some damage to the wall of your blood vessel, then blood is going to start spilling out. Blood pressure, as you may remember, is one of the variables that is maintained by homeostasis. Blood pressure is important to make sure that blood is getting to all the parts of your body. If you don't have enough blood pressure, then it's not going to get to where it needs to go. If you have too much blood pressure, then you're going to have damage occurring to all of your little delicate organs. So you need to have blood pressure within a set range. If you have damage to a blood vessel like this and the blood is spilling out, then you're losing blood. That means that your blood pressure is going to start dropping. If it drops too low, you're not going to have enough blood pressure to maintain blood flow to all your organs and you will die. So it's important to reverse this situation using negative feedback to maintain homeostasis for your blood pressure. So you need to basically form a blood clot to staunch the flow there. So you need a clot so that the blood stops going out. So that's overall a negative feedback loop. You have the stimulus, blood, leaving the blood vessel because of damage in the wall, and then ultimately your response to that is to make a blood clot, and then you don't have any more blood leaving, and your blood pressure is maintained. But you actually have a little positive feedback loop hiding inside of there to make sure that that happens quickly, because it's really important to make sure you don't lose very much blood this way. So it has to be a fast response. So as soon as you have this damage to the wall of the blood vessel, you have these little guys circulating in your blood called platelets. The job of those platelets is basically to stick together and to make the beginnings of a clot. So you're going to have a couple platelets come along. They're going to get stuck to the walls of the blood vessel where it was damaged. Once they're stuck there, they're going to turn on. Once they're turning on, that means that they're going to start secreting chemicals. All these little orange balls are meant to represent chemicals that are being excreted from the platelets. The job of those chemicals is to attract more platelets. So you have more platelets flowing by in the blood, and as they get those little orange ball chemical signals, they're going to turn on and they're going to stick to the platelets that are already there. So now you have some more platelets recruited. They're all sticking to the walls of this damaged vessel. But you need a bunch of platelets to make an actual plug that's going to cover the whole tear there. So all these new platelets that have been activated are now going to start releasing chemicals of their own, and those chemicals are going to attract even more platelets. Then when the new platelets come, they're going to be activated, they're going to start releasing chemicals, that attracts even more platelets. So you're getting more and more and more platelets building up here at this damaged vessel. The more platelets you have, the more chemicals you release, the more platelets you're going to get. And eventually you get enough platelets that the whole tear is completely covered by platelets. And that's the beginning of your clot. Then the body is going to finish making that clot off. So that's a little positive feedback loop that makes sure that this clot forms quickly. That way, overall, you can have your negative feedback loop operating and go back to homeostasis. So that's the basic scheme for how homeostasis is maintained. And then I just wanted to point out that a lot of the variables that are maintained through homeostasis are related to each other and affect each other, which makes it kind of complicated to maintain them all in just the right range. So a good example of that is water. If the water content of your body goes up, that's going to affect the concentration of everything in your blood. So that means that you're going to have a higher pH. The pH is measuring the hydrogen ion concentration of the blood, and a high pH means you have less hydrogen ions. A low pH, which would be acidic, means you have more hydrogen ions. So if you added more water, but you didn't change how many hydrogen ions you have, that means that the concentration of hydrogen ions is going down. And if that concentration is going down, then pH is going up because pH is backwards. The concentration of other ions in your blood, like sodium, chloride, calcium, potassium, those things are all going to be decreasing in concentration if you are adding water. And finally, if you're adding water, some of that water is going to end up in the blood. So now you're going to have more blood, and when you have more blood, the blood pressure will go up. So if you're changing water concentration or the water content of your body, you're going to be changing all these other variables, and there's no way to prevent that from happening. So the brain, which is the main organ in charge of maintaining homeostasis, it has to coordinate all those different variables with each other to make sure that all of them are maintained in the correct range all of the time. It's a big job. And the brain does it real good. But the brain is also maintaining those variables with reference to the external environment or the context of the external environment. So that means that sometimes the brain might get led astray a little bit by things in your environment. For instance, advertisements. So one of the things your brain is doing is maintaining the right concentration of nutrients in your blood. So if the concentration of nutrients in your blood goes down, then your brain is going to make you hungry. So you go and eat some food and get some more nutrients. But the brain is also aware of all the things you're seeing around you. So if you see an ad for delicious cheeseburgers, the brain is going to say, there's cheeseburgers afoot. And it may make you hungry even though you don't have low nutrients in your blood yet, because the brain is just figuring, God knows where the next cheeseburger is coming from. The brain kind of evolved to do these things before there was cheeseburgers and before there was cheeseburger ads, so the system is not working quite perfectly anymore in our modern environment, unfortunately. Homeostasis has a major role to play in a lot of chronic diseases. Broken homeostasis, that is. Homeostasis that is not operating correctly or is not being correctly maintained. So a good example of that is diabetes, in which you have a broken effector. Diabetes involves high blood sugar. Normally the pancreas is controlling your blood sugar in coordination with the brain, and if your blood sugar goes up, the pancreas will release insulin, and insulin tells your cells to take up sugar from the blood so that your blood sugar will go back down. Then if your blood sugar gets too low, the pancreas has a different hormone to release, which is glucagon. That'll bring the blood sugar back up again. So in diabetes, you have some type of a problem with insulin, which is the effector in that feedback loop. High blood sugar would be the stimulus. Then you have receptors in the pancreas that are they're the receptors. They sense how much blood sugar you have. Then the pancreas would be the control center. It starts making insulin as the effector to make the blood sugar go back down. You have a couple types of diabetes. In type 1 diabetes, the issue is that your pancreas is not able to make insulin in the first place. So you're not able to make that effector that would drop your blood sugar back down. In type 2 diabetes, you have insulin resistance, which means that your pancreas is making insulin like normal, at least at first, when you're kind of earlier in the disease, your pancreas is making normal insulin. But your cells don't have the right receptor to respond to it. The receptor they have is broken. So when the insulin comes along in the blood to these cells, the cells can't recognize that the insulin is there, and so they don't respond, and they don't take up the blood sugar. Or they don't take up the sugar from the blood, and then your blood sugar will stay high, even though the pancreas is like really producing insulin and trying. Pancreas is trying. So in either case, the way that we respond to that is by trying to fix that broken negative feedback loop. If you have type 1 or type 2 diabetes, actually, we just basically are giving you insulin. In type 1 diabetes, that basically fixes your problem, well, in a way, patches it up at least. In type 2 diabetes, we may also give you some drugs to try to increase your cell's ability to respond to insulin. And then other than that, we're just trying to give you a bunch of insulin so it kind of a little signal, a little insulin signal that's enough does get through. Another good example of a chronic disease that's based on broken homeostasis is congestive heart failure. In congestive heart failure, your homeostatic negative feedback loops are operating, but not the way that they should be for the situation that you're in, and ultimately it makes the disease worse. So congestive heart failure always begins with some type of damage to the heart that makes your heart weak. It could be a heart attack, it could be an infection in your heart, it could be anything that damages the heart. After you have that damage, the heart is weakened, which means that it's not able to pump blood as well as it was before. So because your heart's not able to pump blood as well, it's going to kind of fill up with too much blood that's getting backed up. So it fills up with blood, it tries to pump it out, but it can only pump out some of it, and then you have more blood coming in, and the heart gets overfilled, and it's not able to contract with enough force to get all that blood out, which means that the cardiac output drops. The cardiac output is how much blood your heart is pumping out per minute. So that is going to go down. Your heart is too weak to pump enough blood. At that point, you're going to have your negative feedback loops kick in to maintain homeostasis. So your body is sensing that the cardiac output has gone down and it knows that needs to be corrected. So it's going to your brain is going to coordinate the response on that to make the cardiac output go back up. And what your brain does to do that is it increases your heart rate. So your heart will be beating faster and therefore pumping more blood. It also raises your blood pressure to make the blood move more quickly. So that will increase your cardiac output in the short term, but you have a problem here anytime you've increased the heart rate. If you increase the heart rate, the heart is going to need more oxygen to meet that greater demand. It's having to work harder, it needs more oxygen. But the heart is already weak. It can't pump enough blood to get enough oxygen to itself. And now it needs more than it needed before. So now your heart is going to be damaged again, and it's going to end up even weaker than it was before. And this cycle is going to repeat and repeat and repeat, and your heart will get weaker each time until it's too weak to pump enough blood to sustain your tissues and you die. So initially, the way our treatment was for congestive heart failure, it was essentially the same as the negative feedback loops that are already operating to make the disease worse. So we would give a person drugs that increase their heart rate, as the person is having not enough cardiac output, and so we figured just the heart is lazy. The heart needs to work harder, so we give some drugs to make the heart work harder, and that helps the person's symptoms at first. They don't get winded as much. They're able to walk more or exercise even without getting so tired for a little bit, and then they get worse. Their symptoms get worse, and then they die faster than they would have without treatment at all. So once we kind of realized that this is what was happening, we changed our entire scheme for treating congestive heart failure. Now congestive heart failure is treated with drugs that prevent the heart from beating quickly. There would be like beta blockers frequently. So you're basically, when the brain sends a signal to tell the heart rate to speed up, it relies on beta receptors in the heart to receive that signal and then speed up. If you have beta blockers, you're preventing those receptors from operating, and so the signal doesn't get through. So the brain is telling the heart, beat faster, but the signal doesn't get through to the heart because of these beta blocker drugs. And so the heart rate does not go up, which means that the heart oxygen demand does not go up. The heart doesn't need more oxygen, and so it's able to sustain itself better and for longer. So homeostasis is so prominent in a lot of these chronic diseases that have become very deadly for our society that we have, in some cases, actually decided to call these diseases homeostatic diseases or diseases of homeostasis. And you have a lot of diseases that fall under that category: obesity, diabetes, hypertension, atherosclerosis, heart failure, autoimmune disorders of all kinds, allergies, asthma, and even psychological disorders like depression. Those are all considered diseases of homeostasis. So in each of those diseases, something is going wrong with homeostasis. Something about it is broken. Maybe you have an effector that's broken, or a receptor that's broken, or maybe you have a negative feedback loop that's operating in a way that is making the situation worse instead of making it better. One way or another, you have failed broken homeostasis in each of these diseases. And another thing you have in each of these diseases actually is inflammation, chronic inflammation. Inflammation is kind of a basic activation of the immune system that involves swelling and the immune cells being activated, and then they start releasing chemicals that promote inflammation. Normally, inflammation is a good thing. If you have like a cut, then you're going to have inflammation in that area, and that's going to make sure that any bacteria that get into your cut are killed by the immune system, and it's also going to make sure that the cells in that area will start dividing, so your cut will heal. So that's good. If it's acute, which means it doesn't last for a long time, then inflammation is usually a good thing. But chronic inflammation is generally not a good thing. It's the opposite of a good thing. When you have this chronic low-level activation of the immune system has a lot of power. It can cause cells to divide, and it can cause cells to die. And if you have that going on when there's not, an infection to clear up or a cut to heal, then it becomes a real problem to have these extra cell divisions and extra cell deaths going on all the time. So inflammation is related to the progression of all of these diseases in some way. It seems to be making them worse. But what's the exact relationship? We don't really know yet. Like, is the inflammation causing the disease? Is the disease causing the inflammation? That we don't know. We just know that it's not good. What does that mean for you? It means exercise as the first thing. Exercise is proven to lower inflammation, and it actually improves the health of almost every organ that you have, including the brain. So it even improves your psychological health. It can help you treat disorders like depression. Why that is, again, we really don't exactly know, but it is clear that exercise lowers inflammation and promotes the health of all your organs. So you should definitely do that. Aerobic exercise is the type of exercise that is associated with lowered inflammation and boosted health for your organs. That is cardio, basically cardio, anything where you're raising your heart rate, where you're sweating, where you're raising your breath rate, so you start breathing faster and deeper, that's cardio. If you're starting an exercise routine, you just want to be careful to go slow and pay attention to your body so you don't hurt yourself. If you feel that something is hurting, even if it only hurts a little bit, stop what you're doing. You want to go slower than that so you don't hurt yourself. It is possible to injure yourself. So just go slow. As long as you're going slow and paying close attention to your body, you should be okay. If you have, like say a heart condition, something that could make it more dangerous for you to exercise, then you want to make sure that you talk to your doctor about it first. But even if that's your situation, it'll still be good for you to exercise. You'll just have to be careful to do something kind of light so you don't aggravate your condition. But literally, even for people who have heart failure, exercise helps their condition. It improves their symptoms and extends their lives. You just have to be careful that you're doing it the right way. And apart from that, just the most important thing about your exercise habit is that you're being consistent with it. And it's not about, how hard you're going, like how far you can run, how fast you can run. It's about the fact that you go to run on like the 3 days a week that you decided that you would, and you do that every week consistently. As long as you're consistent, your habit is going to help you. Apart from that, diet. The main thing you want to avoid in your diet is highly processed foods, which unfortunately is a very large amount of the food that is available to us in America. So that would, processed foods is going to include, anything where you can't tell what part of the plant or what part of the animal it came off of, that's a processed food. So all your cereals, most of your cereals are highly processed, pasta that's processed, bread that's processed. Obviously all of your sweets are processed, processed foods are everywhere, you guys. They're legion. And they're quite bad for you. as the Western diet has kind of spread across the world, so people have kind of given up eating their traditional foods to some extent and started eating, more cheeseburgers and stuff like we do in the West. These homeostatic diseases follow where the Western diet goes. So you can watch rates of cardiovascular disease increase in these countries where they're adopting the Western diet. It's very, very unhealthy. Could even be considered toxic. The most important type of highly processed food to cut out, I mean, I know that's a big ask, don't eat highly processed foods. It's good, any processed food that you can cut out is going to help you. And the best place to start with that is to cut out refined sugars and simple starches. So a simple starch is a starch that is very quickly broken down to sugar by your body. So once you eat it, even though it's not sugar, it will raise your blood sugar very quickly. An example of that would be French fries, actually. Potatoes, even if a potato is not processed, it's that weird vegetable that's actually made of just simple starch, and it does spike your blood sugar. But apart from that, like white bread, yeah, that is not sugar, but it turns into sugar almost as soon as it hits your bloodstream. So if you're eating white bread, you're basically eating sugar. Out of the sugars and simple starches, the most toxic product is sweet drinks. Basically, the more you're spiking your blood sugar, the more quickly you're spiking your blood sugar, the worse for your health. And there is no way to spike your blood sugar faster than drinking a sugary drink, like a soda or even a fruit juice, actually. If your sugar is in a fruit, that is healthy, but if you have made that into a juice, that is not healthy anymore. Short of literally injecting sugar into your bloodstream, there is not a faster way to get it into your body apart from drinking it in a drink. So if that's the one thing if you're only gonna cut out one thing, cut out the sweet drinks. It will help you. Anything that you cut out will help you. They actually have a lot of like sparkling waters these days that don't have sugars but are flavored, so that they taste pretty good, you guys. The Bubbly's a good brand. Coca-Cola has one, like Aha, and they're pretty yummy. They don't have any sugar. They don't have any artificial sweeteners in either. It's just water with some flavoring in it and carbonation. It's really yummy. And that's homeostasis. Oh, no, common misconceptions, haha. So the first common misconception about homeostasis is that negative feedback is bad because it has the word negative in it, and positive feedback is good because it has the word positive. This is not the case. Negative or positive feedback are not necessarily good or bad. Either one of them could be good or bad. It's usually good, or it could be bad if it's, operating inappropriately or if it's broken. Most of the time, homeostasis is relying on negative feedback because that's the type of feedback that returns you to the set point. So negative feedback in general is a good thing. Another misconception is that homeostasis means that your body's internal conditions do not change. So for instance, like your body temperature doesn't change. Actually, everything in your body is always changing all the time. So you're just hovering around a set point. So 98.6 degrees is not the temperature that your body is at, it is the set point for your body temperature. Your temperature is always trying to go back to 98.6 degrees, and it's usually not literally at 98.6. It's always hovering above and below it. Another misconception is that your mechanisms that maintain homeostasis are either on or off, like they are in the diagrams. Actually, they're always kind of on a little bit or on a lot. It's actually very complicated. Another misconception is that every variable in the body is controlled by homeostasis. Actually, very, very many of them are, but not every one. In order for a variable to be controlled through homeostasis, you have to have receptors for it. So if you don't have receptors that can sense where that variable is at, you're not going to be maintaining it through homeostasis. A good example is calcium versus vitamin D. So you have calcium receptors in different parts of your body that can sense how much calcium is in your blood and will respond to make sure it's always at the right level, or just above or below the right level, hovering around the right level. So calcium is a variable that is homeostatically maintained. It has receptors. Vitamin D is a very important vitamin because if you don't have it, you're not able to absorb calcium from your food. Vitamin D is not regulated by homeostasis. That means you don't have receptors for vitamin D anywhere in your body. It's impossible for any part of your body to know how much vitamin D you have at any given time. That means it's impossible to control how much vitamin D you have at any given time.